Hello and welcome to Lesson 10, Part 3. We're going to continue on with our examples, and this next one is going to be pumps. So we're going to look at pumps as links, and then we'll do example 5, and then several examples to come to an elaborate system with a pump. So pumps are modeled as links between two nodes that have pumping curve properties. Each node must have appropriate elevations. A pump is then added as a link, and the pump curve is specified for that pump. The program can operate the pump out of range, but issues warnings to guide the analyst to conceptualization errors. So let's just do it by example. So here's example 5. So we have two reservoirs. The pool elevation difference is 10 meters. In the lower reservoir, there's a suction tube that's 3 meters long, and it descends down into the reservoir, feeds water into a pump, and then that pump pushes water through a 100-meter line into the upper reservoir. The suction side of the pump is a 100-millimeter diameter, 4-meter long ductile iron pipe, so the pump elevation is 3 meters above the pool. It's 1 meter into the pool. The difference in free surface elevation is 10 meters, and the pump performance curve is given by 15 minus 0.1 Q squared, where the added head is in meters and the flow rate is liters per second. Our goal is to estimate the flow rate in the system for this pump to maintain those two reservoir elevations. To do that, we'll need the drawing, which is saved as a bitmap, and we'll get that from the class website in a minute. And we'll need the this information. We'll probably have to flash back to that. And we'll follow our modeling protocol. So we want to sketch the layout on a paper, identify diameters, length, roughness values, identify node elevations and demands, supply reservoir or tank, identify the pool elevations, and identify pumps and supply pump curves in the problem units. So here's the layout on the paper. And in fact, I'll actually screen capture this and do that as the bitmap because it's got lengths that we need, diameters, elevations. The only thing it doesn't have is the roughness height, which is on the next page. So we're going to use a sand roughness of 0.85 in millifeet. So in millimeters. And we'll just put that directly in. And identify the node elevation and demands, supply reservoir elevations. Because we can't enter pump curve directly, we'll just take 3 points off the curve, show them here, and then build and run the model, and we'll see what we get. So there's actually a picture of a screen capture of it right there. So let's go back to this picture, and let's just screen capture that thing as our base map. Capture selection. Grab that. Copy that. That should be all we need. Let's go ahead and bring up our EPANET program. File, new. Let's load in a backdrop. Example 5 layout. And there is our backdrop. We'll go ahead and set our reservoirs. There and there. We will go ahead and put our input and output node for the pump right there. We will Connect that pipe, connect that pipe, and connect the pump. Let's go establish elevations. So this reservoir is total head at elevation 0, done. This has a total elevation of 10, done. This node is located at elevation 3, as is the supply side node, elevation 3. Pipe number 1 is 4 meters long, 100 millimeters in diameter. 0.85 was the roughness value I think that I selected. Pipe number 2 is 100 meters long, 100 millimeters in diameter, and 0.85 was the roughness height. And we now have to specify a pump curve. So we go into data, we choose curves, and we'll create, go to the curve editor, and now we have to enter the 3 points from the pump curve. That happens to be worked out for us right here. So if we put in head of 15 meters, the flow is 0, head of 12.5, it's 5, and 5 is 10. So let us put in those values. 0, 15, 12.5, 5, 0, 5, and 10. We now have a pump curve. Currently I noticed it's in gallons per minute, so we're going to immediately, since we've made that notice, choose the okie dokie. Set the defaults to liters per second, I guess, is the flow units of the pump curve, and we're using Darcy-Weisbach. Lastly, we need to tell it to use pump curve number 1. So we've told pump ID, which happens to be 3, to use pump curve number 1. I believe we're now ready to run our simulation. We've done that. The run is successful. So now when we look at the flow rate, it's 6.16 liters per second operating into the system. We'll go ahead and remove the backdrop. And lo and behold, that is our pump system. Okay, so key things. The pump is treated as a link, and the pump has a curve associated with it. We can name the curve, I believe, my curve, and it's reflected there. And when we look at the pump, we need to tell it to use my curve, and now everything should run just fine. Sure enough. All right, that completes this example. Let's continue. So returning to our presentation, we're now going to look at a network, initially tank supplied, and then we're going to add more to this network. So compute the discharge in each pipe and pressure at each junction for the 8-pipe system shown. The water surface elevation is 315 feet. Prepare the solution, report the results, transmit a letter. So we're going to sketch the layout on paper, identify pipe diameters, length, roughness values, identify node elevations and demands, supply reservoir or tank, identify the reservoir pool elevation, identify pumps and pump curves and the problem units. So here's the layout. These are the various pipe diameters, and what we don't have are the roughness values. This is from an older methodology, so friction factors were supplied. We'll instead have to make a guess at roughness values and adjust them to try to attempt to match these friction factors. We won't be able to do it exactly. Identify the node elevations. identify the tank. I've chosen this way to represent the tank. So the tank connects to node 2. The tank bottom is at the same grade as node 2. It's 120 feet to the bottom of the tank, and then an additional 15 feet to the top of the tank. So this is how I conceptualize the tank. It connects to node 2. I'll assume it's at the same elevation as node 2. Its initial level, its minimum level is 120 feet. Its maximum level is 135 feet. And we'll put it at max level, and that establishes a depth of 315 feet, which I think is the value in the problem statement. Then we define any pumps. There are none, and construct the model and run the simulation. We can adjust inputs until we can get friction factors pretty close to what was shown in the table. We could actually generate an output report. We'll do that when we do it live in a second, and interpret the report. And that would complete that example. So let's go ahead and try to grab the pieces of the example that we need. Mostly I'm going to need that, and I think I'll pull that off the class website. I'm pretty sure I have that bitmap prepped already. So that should be example 6. I do have the bitmap. Download the bad move. One more time. Save tar.js. Alright, so we'll file, new, don't save the changes, load in our backdrop, which is network 6, and we can at least do the layout, and then we'll go back and try to get the other information as possible. So we have junction 1, 2, 3, 4, 5, 6. We have pipe 1, pipe 2, pipe 3, pipe 4, pipe 5, pipe 6, pipe 7. We have tanks you're welcome, and pipe 8. That's all we can do with this picture. Let's see why I suggest that we try to write as much information on the base drawing, at least for this class, that we can. We can now go through this and at least get the pipe lengths and diameters established. So pipe number 1 is 4,000 feet long, 10 inches in diameter, and we use 0.22 as a roughness coefficient. We're going to convert it to Darcy-Weisbach. So that's pipe 1. Pipe number 2 is 6,000 feet long, 10 inches in diameter, 0.22. Pipe number 3 is 6,000 feet long, 12 inches in diameter, 0.22. Pipe number 4 is 6,500 feet long, 24 inches in diameter, 0.22 roughness. Pipe number 5 is 7,000 feet long, 10 inches in diameter, 0.22. Pipe number 6 is 3,000 feet long, 18 inches in diameter, 0.22. And pipe number 7 is 5,000 feet long, 12 inches in diameter, 0.22. And our last one is pipe 8, is 300 feet long, 12 inches in diameter, 0.22. Okay, so our pipes are now established. Next thing we need are the node elevations. Node 1 is at elevation 170. Space demand is 500 gallons per minute. I can't quite fit everything. Okay. Node number 2 is at elevation 180, also 500 gallons per minute. Node number 3 is at elevation 165, 500 gallons per minute. Node number 4 is at 155, 1,500 gallons per minute. Node number 5 is 150, 1,000 gallons per minute. And node number 6 is 145, 1,500 gallons per minute. I believe that is everything we need for our system, except our tank is not specified. So let's go back to our tank conceptualization picture. So the tank elevation, I decided it is at 180 feet. The minimum level is 120 feet above that. The maximum level is 135 feet above that. We'll leave the diameter at 50. And the initial level is 15 level. All right, we'll see if that does what I think it's going to do. Should put the tank pool elevation at 315 feet. We want things in gallons per minute, check, and we want the hydraulics to be Darcy Weisbach. If we run it, we get successful. This time I want to actually plot head. And so the tank head is at 315 feet. And then we have the various heads at the junctions. And we can go ahead and put different graphics if we want. And if flow arrows aren't big enough to see, we'll make them bigger. And so now we have our flow rates in gallons per minute next to the arrows, and we have our head in feet next to the nodes. If we were to plot elevation, here's the elevation. If we were to plot pressure, we would see that our lowest pressure appears to be right here, this node at 49 psi. Okay, so that concludes this example. Now, unlike before, I'm not actually going to destroy this example because I'm going to build upon it in the next example. So the next example uses this as the base, and then it adds to it by by bringing some additional pipes and some pumps into play. So we've essentially done this, and we could adjust the model to, well, let's go ahead and take a look at the friction factor real quick. Computed friction factors, and then we could adjust those as needed if we really wanted to match those that are supplied in the problem statement. We're going to leave it be. The other thing we can do is generate a status report, so let's go ahead and do that live. To do that, you would go to File, Report, Full. We need to give the report a name, so this is example, I think this is example 6, and I'm going to declare it a text file so that I don't have to go finding a text viewer. It should have saved it back to the Playhouse, and it did. And if we open the example 6, it gives us the link node table, the computed results at a node, and the computed results in the link. Actually, it tells us that we're at 15 feet a second coming out of that tank. So we might, let's suppose we don't like that. We want it to be smaller than that. We could certainly change the diameter of that pipe. Let's just double it and see what effect that has. It shouldn't change the flow rate terribly much. So no change in flow rate, but let's take a look at computed velocity. We're now down to 3.9 feet per second. If we go back to 12, 1 foot diameter, rerun it, we're up at 15. So changing the pipe size had a great impact on the velocity. That makes sense. So that would be how we would could generate a status report. If we've actually saved the thing, it would actually regurgitate back the input file. Okay, so the problem is in gallons per minute. So in an old example, I changed it to cubic feet per second. It's unnecessary. Use the flow units that make the most sense for the problem. I find that the pump curves has fewer entries, so if one thing's given in gallons per minute and the other's in cubic feet per second, it's far easier to change a pump curve to agree with the demand units rather than the other way around, because there's fewer numbers to change. So now we're going to take the same system and add a 18-inch diameter pipe boosting from a ground level reservoir at 155 feet into junction node 4, and the booster pump pushes water into the network. 3 points are listed in the figure. Try to determine the flow direction and so forth. So we'd sketch the layout on the paper, identify the pipe diameters and roughness values, identify the node elevations and demands, supply reservoir, pool elevations, pumps and pump curves. So the blue shaded is what we have right now. And so we're now going to want to add these additional parts to it and this additional pipe data. So let's go to the class server, and I'm pretty sure that example 7 is the bitmap we want. Download. We'll put it there. And I'm not sure how it will rescale or not, so we'll see what happens. We're going to unload the backdrop, and we'll load in the network 7. And that should be enough to work with. Let me see if I can mess with the view just a little bit. That's about the best I can do. Okay, so I got the dots. I want to do that so I have some markers. So this loop right here, okay, so we've got node 6. We want to add node 7, 8, and 9. We want to add I have to add a special node here for the pump. Now we want to add pipe 9, 10, 11, 12, 13, 14. Let's kind of tidy this up a little bit to make it sort of look like the picture. There, I like that. We need a reservoir, and we're going to need a pump that connects the reservoir to that pipe. While we're here, we know that the reservoir surface elevation is 155 feet, so let's go ahead and put that in since we have that information right now in the drawing. And that's about all we can do from this drawing. Let's now bring in the pipe data that we can get. Okay, so pipe number 9 is 500 feet long, 18 inches. We'll stick with the same loss as before, 0.22. Done. Pipe number 10 is 4,000 feet long, 10 inches, 0.22. Pipe number 11 is 4,000 feet long, 24 inches, 0.22. Pipe number 12 is 4,000 feet long, 12 inches, 0.22. Pipe number 13 is 3,000 feet long, 8 inches, 0.22. And pipe number 14 is 5,000 feet long, 12 inches, 0.22. Okay, so we've now specified the pipe information. The next thing we have to do is bring in our node information. We only added a couple, 3 nodes, and so node number 6, oh, okay, so this node corresponds to node 7 in the drawing because our tank is a node. So that is at elevation 165, and it has a demand of 500 gallons per minute. Next node is at elevation 170 at 1,000 gallons per minute, and this node here is at elevation 165 at 500 gallons per minute. Okay, so node 11, we have to decide what elevation it's at. So let's look at node 4. It's at elevation 155. Let's make it a horizontal pipe, so it's at elevation 155. That establishes the node elevation, and finally we have to enter the curve for this pump. So we go here to curves, and we will enter the pump curve information that's provided in the problem statement. So we want to use for 0 cubic feet per second, we get 200 feet ahead, 175 feet ahead, and 110 feet ahead, and that's for 0, 10, and 20. The problem is this is in cubic feet per second, but this is in gallons per minute. So we now have to figure out how many gallons or how many cubic feet per second there are, how many gallons per minute there are in a cubic foot per second. Okay, so there's 7.48 gallons in a cubic foot. So if we take 10 times 7.48, that's 74.8 gallons per second, times 60 is 4488 gallons per minute. And then 20 should be twice that. 8976. And now we have our pump curve in the correct flow units. That's what I mean by it's easier to change a pump curve into the flow units rather than those 9 demands. All right, unless I've made a bonehead error somewhere, we should have our system more or less ready to go. There's probably no point in keeping the backdrop, so let me unload it, run our model, and our run was unsuccessful because we didn't supply the head curve to the pump. So we go back to our pump, and we say use curve number 1, rerun it, and our everything is successful. Our pump is boosting 6 gallons per minute into the system. Let's turn our velocity into flow units. There we go. We're boosting 5,340 gallons per minute into node number 4, and you can see how the flow distribution changes compared to the case where if we turn that pump to closed. So if we run it closed, I think what it will do is it will rerun the model. Oh, it's going to force the pump to, there we go. So there's the system with no booster pump in it. Still have adequate pressures, but if we open that pump and rerun it, let's look, let's just keep our eye on node 10 and node 6. So 43 and 51 psi, we rerun it, and now it's 59 and 67. So we've increased the pressure in the entire system by boosting from this reservoir into that system. So that essentially is example 7. We could generate a status report, identify the low pressure node, and we will pick up with example 8 in a subsequent video. That completes this part of the lesson. The